Hello, I'm Achit Nair from Nair's Aviation Ground School. This is the 15th video in a new series of educational aviation videos for the aspiring pilot. In recent videos, we have discussed the engines that power the airplanes that soar through the skies. As a student pilot though, the airplanes you will fly will be basic general aviation aircraft, and these training airplanes will almost always be powered by a piston engine. But in this video, we are focusing on the equipment in front of the engine. This video is about aviation propellers. The propeller has been around in one form or another for more than 2,000 years before the development of successful aircraft. The first description and early development of the propeller for aeronautical applications came about in the late 1400s from the Renaissance luminary Leonardo da Vinci. The development of propellers continued until the introduction of the heavier-than-air aircraft and the dirigible. The Wright brothers pioneered the research and development of the propeller in its modern form. Early attempts at using marine propellers to lift aircraft resulted in failure. The Wright brothers proposed that propellers were nothing more than twisted airfoils, and this idea has been successfully used from the Wright Flyer to the present day. Early aircraft used wooden propellers, with mahogany being the most popular. Propellers made of walnut, ash, oak, and cherry were also used, especially when wartime conditions resulted in a lack of mahogany. In many aircraft today, wooden propellers are still used. An aircraft propeller is an aerodynamic device which converts rotational energy into propulsive force, creating thrust, which is approximately perpendicular to its plane of rotation. The rotational energy can be produced by a piston or gas turbine engine, or in unlimited applications, by an electric motor. A propeller can be attached directly to the crankshaft of a piston aircraft, as in the case of many light general aviation aircraft, or it might be powered through a reduction gearbox, or RBG, which is attached to a piston or jet engine. In this case, the RGB converts the high rotation speed of the engine to one that is more appropriate for propeller operation. Propellers have two or more blades spaced evenly around the hub and are available in fixed pitch or variable pitch configurations. More sophisticated propeller designs include those of the constant speed, contra-rotating, and counter-rotating types. The cross-section of a propeller is similar to that of a low-drag wing and is subject to the same aerodynamic issues such as angle of attack, stall, drag, and airflow. There is a twist along the length of the propeller blade because the blade speed is much higher at the tip than it is at the root of the propeller. The twist is necessary to maintain a more or less constant angle of attack along the length of the blade. Like a wing, propeller performance is degraded when it is not at its optimum angle of attack. To overcome this deficiency, many propellers use a variable pitch mechanism to adjust the blade pitch angle as the engine and aircraft velocity change. Forces acting on the blades of an aircraft propeller include the following. Some of these forces can be arranged to counteract each other, reducing the overall mechanical stresses imposed on the propeller and the aircraft. Thrust bending. Thrust loads on the blades, in reaction to the force pushing the air backwards, act to bend the blades forward. Blades are therefore often raked forwards, such as the outward centrifugal force of rotation acts to bend them backwards, thus balancing out the bending effects. Centrifugal and aerodynamic twisting. A centrifugal twisting force is experienced by any asymmetrical spinning object. In the propeller, it acts to twist the blades to a fine pitch. The aerodynamic center of pressure is therefore usually arranged to be slightly forward of its mechanical center line, creating a twisting moment towards course pitch and counteracting the centrifugal moment. However, in a high-speed dive, the aerodynamic force can change significantly, and moments can become unbalanced. Centrifugal force. The force felt by the blades acting to pull them away from the hub when turning is known as centrifugal force. It can be arranged to help counteract the thrust bending force. Torque bending. Air resistance acting against the blades, combined with the inertial effects, causes propeller blades to bend away from the direction of rotation. Vibratory forces. Many types of disturbance set up vibratory forces in blades. These include aerodynamic excitation, as the blades pass close to the wing and fuselage. Piston engines introduce torque impulses, which may excite vibratory modes of the blades and cause fatigue failures. Fatigue failures are an important aspect to consider when flying aircraft. Torque impulses are not present when using a gas turbine engine in a turboprop. Since the 1940s, propellers and prop fans with swept tips or curved scimitar-shaped blades have been used in high-speed application. This delays the onset of shock waves, where the blade tips approach the speed of sound. Sometimes it is necessary to change the angle or pitch of the propeller to get the most amount of performance out of the aircraft. Variable pitch props are used in many intermediate training aircraft, where the pitch of the propeller is varied at different phases of flight. The constant speed prop is a variable pitch propeller that automatically varies the pitch of the propeller without a change in the selected rotational speed of the propeller. This type automatically adjusts the blade pitch according to the engine speed, thereby maintaining a constant engine speed for any given manual control setting. Constant speed propellers allow the pilot to select a rotational speed according to the need for the maximum engine power or maximum efficiency, and a prop governor acts as a controller to vary the pitch angle of the propeller as required to maintain the selected engine speed. On most variable pitch propellers, the blades can be rotated parallel to the airflow to stop the rotation of the propeller and reduce drag when the engine fails or is deliberately shut down. This is called feathering, a term borrowed from rowing. On single-engine aircraft, whether a powered glider or a turbine-powered aircraft, the effect is to increase the gliding distance of the aircraft. On multi-engine aircraft, feathering the propeller on an inoperative engine reduces drag and helps the aircraft maintain speed and altitude with the other operative engines. In some multi-engine aircraft, the rotational direction of the propellers are different. These propellers are called counter-rotating propellers. These props are used to offset the aerodynamic quirks that occur when the direction of the propeller's rotation affects the flying characteristics of the aircraft. Another form of propellers are the contra-rotating propellers, where there are two sections of propellers on one engine, each rotating in a different direction. This provides the benefits of counter-rotating propellers without the need for another engine. Contra-rotating props were used mainly in older propeller-driven military aircraft and some new high-performance experimental aircraft. The propeller might seem like a small piece of equipment, but the role it played in the aviation world cannot be denied. The propeller provides the thrust for the earliest aircraft, and is still widely used today to power our aircraft. The propeller is an important aspect of the aircraft, and the aspiring pilot should be well aware of the operation of the propeller. For more information, please contact us at liftanddrag@gmail.com and visit our website at niersaviation.webnode.com. Thank you. Safe flying.